Hello guys, welcome to my YouTube channel Vishwaguru, a problem solver. Today's class we are going to discuss a numerical on the topic analysis of perfect frames. By using two methods, we can solve this numerical either by using method of joints or by using method of sections. Preferably, this numerical we are going to solve by using method of sections. Okay, let's go to the numerical. A plane is loaded and supported as shown in figure. Okay, determine the nature and magnitude of the forces in the members 1, 2, 3. Okay, here you can see this is the frame is given. Here the forces in the member 1, 2, 3. This we have to calculate. And this one supported at both ends as mentioned. So the reactions at point A and B that we have to calculate first. And at point D, there is a point downward load. 1500 Newton is acting. Okay. So here, first thing, we have to calculate the reaction. Okay. So the reaction calculations. This will be the reaction at point A or A. This is reaction at point B or B. Okay. So reaction calculation. Actually, if here the consideration is this beam that should be, that means this frame that should be in equilibrium. Okay. If it is in equilibrium, then we can use the equilibrium principles such as summation of vertical zero, summation of horizontal zero, summation of moment about any point equal to zero. Here we are going to, here there is no horizontal forces. So we are going to consider the summation of vertical equal to zero, summation of moment about the point, any point, preferably from the point A that equal to zero. Okay. So summation of the vertical forces equal to zero. Okay. So here you can see RA and RB. These two are the upward force. 1500, that will be a downward force. So we can say RA plus RB that equal to 1500. This will be the first equation. Then algebraic sum of the moments about any point, here preferably from the point A, and equate that to 0. Okay. When you take moment about point A, here there are three loads are there. RA is acting exactly at the point A. So moment made by that reaction force RA, that will be eliminated. Okay. So moment made by the other two forces that we have to consider. Here from the point A, this is 1500 Newton and the perpendicular distance will be A. This 1500 multiplied with A. And here you can see this 1500 into A. This moment will be in clockwise direction with respect to the point A. So 1500 multiplied with small a, the distance. This will be in clockwise. So this will be counterbalanced by the moment made by the reaction force RB. So here RB, this is an upward force. So with respect to point A, this will be in counterclockwise. Okay. RB multiplied with 4A. Okay. This will be in counterclockwise direction. Here, this unknown distance, but whatever, this A and this A we can cancel. So we can write RB that equal to 1500 divided by 4. So we will get RB equal to 375 Newton. Okay. Then substitute the value of RB in first equation. Then we will get RA, which is equal to 1500 minus 375. We will get 1125 Newton. Okay. So now we calculated the reactions. And then here, many right angle triangles you can see. And moreover, this angle theta is we are going to calculate initially, because to calculate the moments somewhere else, here we need the angle. Okay, because sometimes this distance LM is needed. Okay, so to calculate this, the angle theta is needed in this numerical. So it's better calculate the angle initially. What is this angle? Okay, so here from the right angle triangle, here I'm going to take the right angle triangle ACE, because for this only this 2.25A that we know. Actually, guys, this 2.25A, this is vertical distance. It's not the length or something of CB. This is the distance of CE, the vertical distance, or we can say the projected vertical projection of CB. That will be on CE only. Okay. So the CE, that distance will be 2.25. So from the right angle triangle AEC, okay, here this angle, and we need the value of this theta. Here the two known facts, that means AE. AE is the known value because that will be 3 times the A, and the vertical value distance CE, that is 2.25A. So here for this theta, the CE will be opposite side, AE will be adjacent side for this right angle triangle AEC. So we can take tan theta preferably, that equal to opposite side by adjacent side. Here the opposite side is CE divided by the adjacent side, that is AE. So tan theta equal to CE, that is 2.25A divided by AE, that is 3 times the A. So this A and A we can cancel. 2.25 divided by 3, and we have to calculate theta, that is tan inverse of 2.25 divided by 3. Okay, if you simplify 2.25 divided by 3, we will get 0.75. Then the tan inverse of 0.75. Okay, that is theta is tan inverse of 0.75. We will get the angle theta equal 36.87 degree. Okay, so this will be used in the numericals. Okay, so here then, as I mentioned earlier, this we can solve by using both the methods, by using method of joint or method of section. But method of joint means like we have to start from each joint, joint A, D, like that we have to go to calculate the forces in this particular members 1, 2, 3. Okay, so it is tedious and it will be a lengthy one. So here we are going to solve by using method of sections. Okay, method of sections. And we know that we go to draw the section line. That section line I'm going to draw here. Okay, that which passes through the members 1, 2, 3. That is DL is 1 here, LM that is 2, ME that is 3. Okay, so this section line 1, 1 that passes through the members 1, 2, 3, the required members. Okay, so here the section line passes through the members section line 1, 1. Okay, and as usual, when you draw the section line 1, 1, cut the frame into 2 portions. Here we can consider any half. Okay, that is the left side portion or right side portion. Here I am going to consider the left side portion. Okay, so left side portion of the section line 1 1 that we are going to consider. Okay, so here you can see, as usual, the point loads. What are all the point loads which are all acting in the considered portion that we have to consider, like 1500 Newton and the RA. These two are acting in the considered portion. The RB is not acting in the considered portion, so that we are not going to calculate. That means that we are not going to consider, okay, in this calculation. So these 2 point loads and the members, the forces in the members in which the section line passed through, like 1, 2, 3, that is LD, LM, ME. Forces in these 3 members only we have to consider, like AD, DM. If you put some points, these members and all not cut by the section line. These are all the whole members. Even though these members, which are all not cut by the section line, they are in the portion, that means the left side portion, which we are going to consider. These members, whole members, which are all not cut by the section line, that we are not going to consider. That means that forces in the members we are not going to consider for the calculation. Okay, so this 1500 Newton RA and forces in the members 1, 2, 3. These 5 forces we are going to consider here. Okay, so here first I am going to take moment about other points. That means here, first thing, here there are 3 unknowns are there. So we got to choose the point, like it has to cancel moments of any 2, at least any 2, okay, of the unknowns. Okay, so first here I am going to take moment about A. Okay, when I'm taking moment about A, here you can see the RA that will be eliminated. And then this ME, actually guys, here the force in the member ME, this one is a horizontal force. This horizontal force means that we can consider, for an example, this ME, it may act this direction or otherwise this direction, whatever. But it is a horizontal force. So it passes through point E, it passes through point M, even it passes through point A also. Do you understand? So when I take moment about A, this will be eliminated. Okay, when I take moment about the point and equate to 0, because as per the equilibrium principle, here if you calculate moment about any point, that should be equal to 0. So here you can see, when I take moment about A, the moment made by the force in the member ME, that is 3, that will be eliminated, because the line of action of the force F3 that passes through A also. Then what about this one, F1? Same way, this may be this direction or otherwise this may be this direction. That is unknown, but that line of action of the force F1, that also passes through the point A. So that will also be eliminated. Okay, so this unknown F1 and F3 will be eliminated. The only thing is this force in the member F2. Okay, that means force in the member LM, F2. That only we are going to consider. Okay, when you take moment about A and equal to 0, the moment made by the RA, that will be eliminated first of all. This 1500 multiplied with A, 1500 multiplied with A, this will be in clockwise direction. So 1500 multiplied with A, this will be in clockwise moment, then that equal to, here among 5 forces, this RA is eliminated because that line, that means that is exactly acting at point A. This F1, force in the member DL, that line passes through A, that also eliminated. This ME, the force in the member ME, F3, that also passes through the point A, that also eliminated. So the remaining one, that is F2. It may be upward or downward. Okay, it may be upward or downward. For an example, if it is downward, then with respect to point A, this F2 multiplied with the distance, perpendicular distance 2A, F2 into 2A, that will be also in clockwise, which cannot counterbalance the clockwise moment made by the point load 1500 Newton. So it is not possible acting downward. That means it should be upward or outwards from the point M. Okay. So this will be the direction of M. Then F2 multiplied with 2A. That will be in counterclockwise direction. Okay. So F2 multiplied with the distance 2A. So here this A and A we can cancel. So we can write F2 equal 1500 divided by 2. So we will get F2 that equal to 750 Newton. Okay. So we got the value of F2, that is 750 Newton. That means if this is clockwise, this will be counterclockwise. Okay. So we got the value of one unknown. Then we got to calculate the values of F1 and F3. Okay. So here, next I'm going to take moment about L. Okay. Summation of moment about L and equate to 0. Okay. When I take moment about L, these two forces like F1 that passes through L, F2 that is also passes through L. So these two will be eliminated. Okay. Remain 3 we have to calculate. And here you can see this ME, as I mentioned earlier, it may act towards right side or left side, whatever. From the point L, this LM will be the perpendicular distance. This will be the moment. This will be the direction of the force, but the LM will be the distance. So here, first we have to calculate LM. Okay. So here you can see, I'm going to consider the right angle triangle ALM. That means AML. Okay. Here, the right angle triangle AML. Okay. The right angle triangle AML. Here we need the value of opposite side LM. And we know the value of horizontal and then the angle. So again, tan theta. Opposite side ML by adjacent side AM. Opposite side we don't know. So we can write ML or LM that equal to AM tan theta, where AM that is 2 times the A. Tan theta already we calculated. The theta that is tan 36.87 degree. From this, we will get the value of LM. Okay. The value of LM that will be 1.5A. Okay. That is 1.5A. So ML or LM we calculated. So now taking moment about L and equate to 0. As I mentioned earlier, F1, F2 will be eliminated. The remaining 3 forces we have to consider. This is RA. From the point L means that is in point M. Okay. So this is the distance 2A and this will act. That means I just explained like this also. This is the direction of RA. Here you can see this is at a distance from L, that is 2A. Okay, at a distance 2a. Okay, so RA multiplied with the distance 2a from L. RA into 2a. RA into 2a. This is in clockwise direction. Okay, I just erase this to avoid more lines. Okay, I just put that for only understanding purpose. So RA multiplied with 2a. This is in clockwise direction. Okay, this 1500 multiplied with a from the point L, 1500, because this distance, that is a perpendicular distance, 1500 multiplied by a. This will be in counterclockwise. Thus, I put this side. Okay, that is 1500 multiplied with a. This one counterclockwise direction. Okay, so here you can see one moment made by the reaction force, that is RA into 2A, that is in clockwise direction. Other moment 1500 into A, that will be counterclockwise. Here RA value we know, we calculated already, that is 1125. If it is multiplied with the 2A, you will get 2250 A, but this will be 1500 A. So you know that this one, that will be greater than the counterclockwise moment. So here clockwise moment is more than counterclockwise moment. So another counterclockwise moment is needed to compensate this clockwise moment, because this is greater. Okay, as per the equilibrium principle, both should be same. Clockwise moment, that should be equal to counterclockwise moment. Here clockwise is greater than counterclockwise. So the moment made by the force F3 in the member ME, that should be in counterclockwise direction. Okay, that should be added here. Here, as I mentioned earlier, this ME, it may act this direction or this direction. If it act inwards to M, then we know that it will be like this. From the point L, this force F3, if it acts this direction, that force into LM, that will be in clockwise. So it will not act this direction. This should act in outwards from the point M. Then from the point L, this will act in counterclockwise direction. Okay, so that I am going to substitute this side. That is force in the member F3, the perpendicular distance from L. Okay, this is the line of action of the force F3. This is the perpendicular distance LM, which we calculated already 1.5A. Okay, so that will be F3 multiplied with 1.5A. Okay, so here we know the value of RA. We know the value of, that means all other values we know. So only unknown is F3. So from this F3 that we can get, okay, F3 that we can get, that is 500 Newton. Okay, so as of now, we calculated two forces, okay, among three unknowns. Okay, then remain one. What we have to calculate, that is F1. To calculate F1, I am going to take moment about the point M. Okay, I am going to take moment about M and that equal to 0. Okay, here you can see when I take moment about M, these two forces F2 and F3, both are all acting from the point M. So moment made by these two forces F2, F3, that will be eliminated. Okay, so the other three forces, that is moment made by the other three forces, we have to consider. Here F1, that is an unknown force. Okay, so first thing, when I take moment from point M, this RA multiplied with 2A, that will be in clockwise direction. Okay, RA into 2A. That will be in clockwise direction. 1500 multiplied with this A. That will be in counterclockwise direction. Okay, that first I'm going to write as summation of moment equal to 0. That is RA multiplied with 2A. Okay, that is in clockwise direction. And then this 1500 multiplied with A. That will be in counterclockwise direction. When I take moment from M, that will be in counterclockwise. Here you can see this 1500, this RA, the value of RA, that is 1125. So you know that this will be 2250A. This will be 1500A. So you know that clockwise moment, that is greater than the counterclockwise moment. So the moment made by the another force, F1, force in the member DL, that should be in counterclockwise, then only this will be balanced. Okay. So for an example, here this F1, if you consider this is acting this direction, you can consider this is acting through point L also. Okay, the F1 is acting at point D, passes through A, passes through L, passes through C, because the line of action of F1, that is same here, A, D, L, C. So here I'm going to consider this F1 is acting through point L. If it is acting from the point L, that we have one vertical component and one horizontal component. Whatever the vertical will be eliminated. If you consider this is acting outward from the point D or outward from point L like this, then the horizontal component F1 cos theta, that will be towards right side, because this will be in first quadrant. So that will be towards right side. So when you take moment about M, that F cos theta multiplied with the distance, that is LM, that will be in clockwise direction. But here we need counterclockwise moment. So it will not act like this. It will act opposite to this direction. That means like this. That means in the third quadrant, it is going to act. As I mentioned earlier, this act inverse to the point D or outward from point L, whatever. Okay. So here, I'm going to consider this force is acting from the point L also. Okay. If it acts this direction, that will be F1. For the difference, I just drawn with a different color. Okay. Here you can see it is at an angle theta. So if this is the force F1, this will be the horizontal force, that is F1 cos theta. And this will be the vertical force F sin theta, F1 sin theta. Okay. This F1 sin theta passes through M. F1 sin theta passes through M. So when I take moment about M, that F1 sin theta or moment made by F1 sin theta will be eliminated. So F1 cos theta multiplied with the distance, perpendicular distance LM. When you take moment about M, LM will be the perpendicular distance. This will be F1. So F1 into LM. Okay, F1 into LM. That I'm going to substitute here. Sorry, F1 cos theta. F1 cos theta. This one, F1 cos theta. The horizontal component is F1 cos theta multiplied with the distance LM. Here we calculated the LM, that is already 1.5A. If you substitute and the theta values we know, if you simplify everything, we will get the value of F1 that equal to 625 Newton. Okay. So now all the unknowns we calculated. Okay. That means here you can see for the point D, it will be inward. For point L, it will be also inward. Okay. So it will be tensile in nature. For point M, it is outward. So from point L also, it will be outward. From point M, it is outward. So from point E also, it will be outward. Okay. So next, I'm going to draw the force table. Okay. So the force table, serial number, the members. Actually, here many members are there, but only we have to calculate forces in the member 1, 2, 3. That only here we are going to substitute. Magnitude. All the values are in Newton that I'm going to put here commonly. Then nature, either compressive or tensile. First one, that is the member F1. We know the value of F1 recently that we calculated, that is 625. Here you can see F1. From point D, it is inward. From point L also, for the point L also, it is inward. So here, this tended to pull the member DL. So that is tensile in nature. Second one, that is F2. Force in the member LM. That is F1 is DL, F2. That is LM or ML, whatever. Here we calculated the value of F2, that is 750 Newton. Here you can see from the point L it is outward, from the point M it is outward. Both are in, that means tend to compress the member. So the 750 Newton, and it will be compressive in nature. Okay. Then the third one, F3, force in the member ME. We calculated this value, that is 500 Newton. Here you can see from the point M, it is going outward. From the point E also, it is going outward. So it is tended to compress ME. So it will be compressive in nature. Okay. Okay, guys. So all the three unknowns, required values we calculated. I hope you all understand this video. For more number of videos, don't forget to subscribe my YouTube channel, Vishwaguru, a problem solver. Okay. Thank you, guys. Thanks for watching.